This video is about nuclear radius and nuclear density. Let's begin by examining the nuclear radius. Logically, the volume of a nucleus, V, is proportional to its nucleon number, A, so we can write that V is proportional to A. Assuming that the nucleus is a sphere, we can write that V is proportional to R cubed, where R is the nuclear radius. Combining our two expressions, we get that R cubed is proportional to A, and taking the cube root on both sides gives us that R is proportional to the cube root of A, or A to the power of 1/3. This relationship can be expressed using the following formula. Here are the variables that are present in this formula. R0, the Fermi radius, is found experimentally. An important point to remember here is that the Fermi radius is related to the size of the nucleus, while the Bohr radius is related to the size of the atom. While the order of magnitude of the Fermi radius is 10 to the power of -15, the order of magnitude of the Bohr radius is 10 to the power of -10. Next, let's look at nuclear density. Density, ρ, is equal to mass divided by volume. The mass of a nucleus is equal to the nucleon number, so A, multiplied by the unified atomic mass, so U. This is divided by the volume of the nucleus, and since we assume that the nucleus is a sphere, here we get 4/3 times pi multiplied by the nuclear radius cubed. I will substitute R0 times A to the power of 1/3 for the nuclear radius, which gives us R0 times A to the power of 1/3 to the power of 3. Bringing the 3 up from the denominator into the numerator and expanding the parentheses, we get 3 times AU divided by 4 pi times R0 cubed times A. Let's cancel A and substitute. This gives us 3 times 1.661 times 10 to the power of -27 divided by 4 pi times 1.2 times 10 to the power of -15 to the power of 3. Carrying out this calculation gives us that the density of the nucleus is approximately 2.3 times 10 to the power of 17 kilograms per cubic meter. This number shows us that the nucleus is extremely dense. For example, 1 cubic centimeter of this material would have a mass of over 200,000 tons. The only other object in the universe that has approximately the same density is a neutron star. This completes our discussion of nuclear radius and nuclear density. In the next video, we'll learn about electron diffraction.